So now you know about the idea of a smooth function. You know what a smooth function is. We know how to prove a function is smooth. I'm going to need some more machinery to make this work. But I thought before I get too into the nitty-gritties of the weeds of all this stuff, I thought it would be a good idea. I'm just going to show you what the end goal is here, okay? We'll come to the actual proof for this, but I want to make sure you are aware of what we're trying to aim for. And it's going to be akin to the same thing we talked about just earlier. So this is what so this is our goal here. So this is going to be the goal that we're going to try to reach. So let there be complexity functions f and g. So I suppose I have these two functions. So suppose that I had the following right here. Suppose I have f is big O of g. But it's the case that n is a power of an integer constant. B greater or equal to 2. So suppose that I showed you that f is big O of g with this restriction on the input. I must stress that there's other restrictions you may have, but this is the one that is specific for the proof that I'm going to be showing you. There's other ones that exist. I have an example in the notes. For example, if you want to have it where n is a multiplicative constant of b, there is other ways you can characterize this. So for example, if you want to make sure that n is always even or something, you can do things like that. But I'm going to focus on this one because it's a very common form for algorithms that take on the divide and conquer pattern, or the paradigm of divide and conquer. So here's the condition that makes this work. So remember how I told you that there's some condition that I can use to go from this to just this. So I want to be able to just say f is big O of g without having to say that n is some specific inputs. So here's the condition that I'm going to be getting to. So this is what I would like to show, is that if you have this in place, then you can automatically go from here to there. And this is actually what we're going to call the smoothness rule. So what I'm going to be trying to do is proving this thing called the smoothness rule. That's the goal. So presuming that f is asymptotically non-decreasing, so I've defined this already. Asymptotic. It's always, all right. I was wondering why it's a little bit funny here. Asymptotic, there we go, is asymptotically non-decreasing. And it has to be, so f is asymptotically non-decreasing. That's all you need for it to work. And g is smooth. So as long as you have these two things in place, so if you have this and you have this, so f is asymptotically non-decreasing and the g is smooth, which remember, g meaning it's smooth means it's asymptotically non-decreasing. And as we've seen before, that f of 2n is big O of n. So big O of f of n, sorry, f of n. If we have these two properties, then we can go from here to there. You don't have to do any other work than just invoking this smoothness rule, as long as you know that you have these two properties. So this is a very nice shortcut for your analysis. And I got to show you how you go from here to there. That's my goal. So this is what we call the smoothness rule. So my goal here is I'm going to prove to you the smoothness rule. But to do this, I need some more machinery to make that work. That dreaded M word, that mayonnaise, mustard, or whatever it is. Miss Kitty, I'm not quite sure. So we're going to need some more terminology to make this work, for at least this setup. There's other ways you can prove different kinds of smoothness rules, but this is going to be the one we're going to focus on. So let's lay out some more things for us. So you might say, Dan, you gave us a definition for smooth, that f of, remember, f has to be asymptotically non-decreasing, and it has to be the f of 2n is big O of f of n. But I need another concept that's going to generalize over the idea of smooth. So the first thing I need to tell you is that being a smooth function actually generalizes to an even stronger condition. So that's going to be the first claim I'm going to have here. So we're going to define something called b-smooth. You know, b-smooth. Be smooth today, guys. So at first, this is going to look like it's a generalization of the idea of smooth, but I'm actually going to prove to you that any function that is smooth is b-smooth. So this is just, so we say a complexity function, function f, that is both, so you're going to see that this definition is just like the smooth definition with a small wrinkle. It's both, one, asymptotically non-decreasing, and it has to be that f of bn is big O of f of n. And this has to be for every integer constant b greater or equal to 2. So just keep in mind that the b is within the input of the function. So it's b times n here. It's just like we had for our smooth function, it was just 2n. I'm saying it's bn. The b is not a multiplicative factor here. It's inside, which makes it look a little bit stranger than what we might be used to. So this is going to be, so what the next claim we're going to prove is going to be a vital ingredient for proving the smoothness rule. So here's a theorem. So hopefully you can follow along with me on this one. And it's going to be using something called mathematical induction. So I might need to get some help in a little bit from our lovely furry friends. So if a complexity function f is smooth, then f is b-smooth. So that's the claim. So and if you give me a smooth function, it has to be b-smooth. So we're going to start this proof up, okay? There's going to be some moving parts to this, so you have to make sure you follow this very carefully. So what we're going to do is we're going to make use of mathematical induction, the principle of mathematical induction. So I'm going to give you an idea of how this proof will get laid out. And it's going to use the principle of mathematical induction to work. So I'll give you an idea of how this will get set up with the induction in a moment. So I'm just going to start off by denoting what exactly we're going to prove. For any integer b greater or equal to 2, let b of b, so capital B of lowercase b, denote the statement b of b, where f of bn is big O of f of n. So I'm going to presume that the function f is smooth. So our goal is if f is smooth, then it has to be that this is true for each value of b. So technically I could have said if f is smooth, then this, but the setup of this proof is pretty darn straightforward. So I'm going to start off by trying to show this for a small value for b. So I'm going to start off with step b is equal to 2. So what I'm going to first do is I'm going to show you this, what we're going to call the base step. And then I'll give you the idea of how induction works, and I'm going to get some help from Miss Kitty. So remember that if I have b is equal to 2, notice that that's just the definition. This is just saying it's smooth, right? So we don't have to do anything. Since f is smooth, f of 2n is big O of f of n, right? Proving b of 2, right? It's pretty darn straightforward. I don't like using those phrases, but it is a tautology, right? Like so we know f is smooth, and we're given literally the second condition of what makes a smooth function. So this brings me to the part where it really matters, where we have to start being a bit more careful about how we carry out mathematical induction. So I'm going to need some help from my lovely assistant here, Miss Kitty. She might be a little bit pissed off. So let me just grab Miss Kitty here. Okay, come on, Miss Kitty. Here we go. We got Miss Kitty. So Miss Kitty is going to help me teach us how we would carry out this mathematical induction proof. Everybody say hi to Miss Kitty. Hello. There's Miss Kitty. Yeah, she's looking a little grumpy here at the moment. At least I think. She might be in a pleasant mood. I'm not quite sure. Oh, she just woke up from a nap. Okay. That would explain everything. She's looking a little sleepy here. So what we're going to do is to teach us mathematical induction. We started off with b is equal to 2. I would like to show this for all b is greater or equal to 2. So I know how to do it for the first rung of the statement. So I want to imagine it like I'm trying to teach Miss Kitty how to climb up a ladder to the top of the bunk bed to get back to her nap, okay? So I have b is equal to 2, so I know how to get Miss Kitty up one rung. I need to show how I could give you an arbitrary rung of this ladder for any one of these values of b, how to go from b of 2, for example, to go to b of 3, to go from b of 3 to b of 4, to b of 4 to b of 5. So I'm going to use induction based on any one rung, and I'm going to show you how to get to the next rung so I can show Miss Kitty how to climb any one arbitrary rung in the ladder. And then by doing that, we'll be able to show Miss Kitty how to get back up to her bed to have her nap. Does that sound okay, Miss Kitty? I think she agrees. So Miss Kitty was very thankful for you to help us out. I don't know if you want to hang out, but I'm going to do now the induction step, Miss Kitty, okay? So thank you so much, Miss Kitty. Thank you for all your help. I'll let you get back to your nap, okay? Okay, here you go, Miss Kitty. There we go. Everybody give thanks for Miss Kitty. Miss Kitty is helping us learn about mathematical induction here and how we're going to use it. So let's go to the actual induction part of this proof. So we know how to do it. We know how to prove the statement for b is equal to 2. So the idea in mathematical induction is I would like to show you if I know if the previous statement is true, so for example, b of 2 is true, how can I use that to prove b of 3 is true? And if I have b of 3, then most certainly I can show you how b of 4 is true. Almost like I'm lining up dominoes, or in this case, helping Miss Kitty climb up a ladder by showing you teaching her how to climb up one rung in the ladder. So if you have that, then you could start at b of 2, go b of 3, b of 4, and you can show how to go up any one rung in the ladder and help Miss Kitty get to her napping spot, okay? So let's do the induction step. So we're going to be proving that b of k, if b of k is true, then b of k plus 1 has to follow from it. So we're going to fix some k greater or equal to 2. I usually use a different variable for this as opposed to lowercase b, because I want to be able to fix this value of k and be able to play around with it for an arbitrary k. This is in contrast to the way I parameterize b over there, but in most senses, a lot of people won't make any delineation between these two things. That's okay. I just like to be a bit more precise about how I formulate the induction step. And I'm going to assume what we call the induction hypothesis or the inductive hypothesis. This is just the previous rung in the ladder. So this is the one that Miss Kitty's going to put her foot on to get up to the next rung. and assume that b of k, or f of kn, is big O of f of n. So this is what we call the induction hypothesis. And I would like to be able to, I'm going to presume this because if I have, say, if I want to prove that b of 3 is true, then I'm going to presume that b of 2 is true because I already showed you b of 2 is true. So the idea is I'm going to show you from any one previous rung how to get to the next one. But the idea is I must use the previous statement to help me get there. That's at least the way I'm using the induction here. So I'm going to presume that this holds. There's a lot of ways this could go wrong if you do not set this up properly. So if you're misusing induction, this is how you set up the induction here. You can't just assume any one of them is true without an appropriate setup here. You have to be careful because we're going to invoke the principle of mathematical induction at the end. So it has to be that one follows from the next. So just watch carefully how I do this. So we will show that b of k plus 1, which this is saying f of k plus 1 times n, is big O of f of n. That's what b of k plus 1 says. We will show that b of k plus 1 also holds. So that's what we're going to be trying to do. If we could do this, then we can use the principle of mathematical induction and complete our claim. That f, if it's smooth, then it has to be b-smooth. So remember that because f is a smooth function, it has to be asymptotically non-decreasing. So I'm going to use that fact. So I'm going to say function f asymptotically non-decreasing. So for sufficiently large n, and I must stress that you could give this a name. I'm not going to here, but I'll just give it, I'm just going to use it in the appropriate way so that I'm just trying to make this a little easier for us so we don't have to make more names for variables. But the asymptotic non-decreasing function definition says that there's a sufficiently large n, which we called in that definition n0, large n, that f of k plus 1 times n is less than or equal to f of 2kn. So this is a claim I'm going to make, is that f is asymptotically non-decreasing. So if there's a sufficiently large value of n such that if I put in the input k plus 1 times n, it's going to be that it's less than or equal to f of 2 times k times n. So watch how I get this. Because remember, it's asymptotically non-decreasing. Remember, the shape of the function will be that it goes up or it gets flat. So watch this. So I'm just going to look at their inputs because that's what an asymptotic non-decreasing function allows me to do. Since k plus 1, remember that's this right here. Remember, it's k plus 1 times n, 2k times n, right? So I'm just going to look at the k plus 1 and the 2k. Sorry, yeah. It's less or equal to 2k, which this is no different than me writing that 2k minus k plus 1 is greater or equal to 0, which this is no different than me writing k minus 1 is greater or equal to 0. So since this is the case, since this is true for all k greater or equal to 2, right? So this has to be true, like this statement right here has to be true for all k's greater or equal to 2, which is all you need, right? Because remember, the statement involves b being greater or equal to 2. So that's all you need here to make this work. So I'm just looking at the input. So the idea here is that if I have this bound in place, then I should be able to massage this in terms of big O. So this is how we're going to use this. So watch this carefully. So I'm just going to use the smoothness of f to do the following very crafty step here because of this property. Then, by the smoothness of f, because remember f is smooth, we get the following. So let me just finish up the proof over here. We're almost done. So there's a very slick step that's going to happen. It's due to the big O notation. And there's a reason why I wanted that 2 there. So watch this. Because remember, our definition of smooth had this 2 in there, right? So it was 2 times the input is big O of the function, which is the thing itself, right? So we're going to use that. So then by the smoothness of f, we get the following. F of k plus 1 times n is less than or equal to f of 2kn, which this is equal to, I'm just going to rewrite it in a way that's a little bit easier for you to see what's going to happen, is 2 times kn. But I'm putting the kn together and I'm multiplying it by 2. But here's the thing. If I have the function, and suppose this is the input of that function, what can I say about this in terms of big O? Well, because f is smooth, I can drop the 2. So I have f of kn. And yes, I will not read that out loud, okay? F of kn. I'm not going to try to abridge that description. But what does this mean? That implies that there's actually those 2 constants that are going to exist for the definition of big O to work, right? Implying the existence of constants. This is why I just need it to be sufficiently large for the value of n. Because at the end of the day, if I get this right here, then I could just tell you that these constants exist. This is why I didn't introduce another name, because I was just going to have some more, that's just some bookkeeping that isn't going to matter much at the end. Implying the existence of constants. C1, which is going to be a positive real constant, and N1, which is going to be a positive integer, such that for all n greater or equal to N1, that's important, it's not N0, I haven't talked about N0 yet, N1, that it has to be that f of k plus 1 times n, all in the input there, is less than or equal to C1 times f of kn. That step's a very clever little step here, but this is what we need to get our key ingredient for the induction step. Why? Well, if you look at this very carefully, you actually can see that I actually have we have something that looks like our induction hypothesis, or the inductive hypothesis. It's just sitting right here, right? It looks eerily similar to this, right? So that's what I'm going to do, is I'm going to use this fact. So by the induction hypothesis, so I'm going to show you how you take a statement involving b of k, and I'm going to show you how you show that b of k plus 1 also holds, presuming that b of k holds. By the induction hypothesis, f of kn is big O of f of n, right? So there are constants C2, which is a positive real number, and N2, which is going to be a positive integer. where it has to be that f of kn is less than or equal to C2 times f of n for all n greater or equal to n2. So this is rather interesting. So notice that I have something that says f of kn, and I have something that says f of kn, and I also have f of n right here. Notice that I would like to bridge this to connect it up with this. If I could connect those two together, we're done. So I'm going to use a little bit of bounding tricks here to find an appropriate constant for c to complete our proof. So now I have this and this to play around with. So watch this. By selecting constants, so I'm going to pick c to be C1 times C2. This is a very common trick for proving big O identities. C1 times C2, and I'm going to make N0 be the maximum, the larger of the two of N1 and N2. The reason why is because I would like to make use of these two inequalities here. So if I make N0 big enough that it subsumes both of them, meaning that both these have to be true, then we're okay. I can use them if I make N0 big enough. Then, notice here, so watch this, watch this. Okay, so I have f of kn is less than or equal to, so remember we have this over here, right? So we have f of k plus 1 times n. That's less or equal to c1 times f of kn. Well, you would agree with me that f of kn is less or equal to c2 times f of n. So most certainly, what I could do is put this inequality, just like put this right here. Like just try, okay, so I know this is going to need a c1 right here to make this work. So I multiply both sides of this by c1. And then I could put this right here. Then f of k plus 1 times n is less than or equal to c1 times f of kn, right? Which this is less than or equal to c1 times c2 times f of n. But this is right here c, right? So that's equal to c times f of n. And this holds for all n greater or equal to n0. But what is this statement? This statement is b of k plus 1, right? We've proven b of k plus 1. Which proves b of k plus 1, completing the induction step. Now, I could use the principle of mathematical induction and we're done. Therefore, by the principle of mathematical induction, I'm just going to abbreviate it as PMI. B of B is true for all B greater or equal to 2, which proves the claim, and we're done. So are there any questions about that? So this is the first key ingredient for proving the smoothness rule, is that we show that every smooth function, so if a function is smooth, then it has to follow that it is b-smooth. We're going to need this b-smoothness property for what we would like to prove next. So one thing I can mention is that you can actually simplify this proof a little further. If you analyze the proof for the transitive property of the one I talked about earlier on in this session, which I will show you that proof at some point. It'll be somewhere out there. If you have that, you'll notice actually it's buried in this proof right about here. So you can actually simplify this proof by invoking the transitive property of big O. That big O is transitive. It's transitivity of big O. So now we know that, so the big recap for where we are is we know all smooth functions, they are b-smooth. So if I give you a smooth function, you could say it's b-smooth. And now we could prove the smoothness rule. So let's now do that. So now we have the key ingredient. Isn't that exciting? So we've actually characterized smooth functions using a much more general property, which is kind of interesting in its own right? It shows you that the simple definition of being smooth characterizes actually quite a bit. It's actually a really nice, simple definition, which I think is kind of surprising the first time I seen it. So just to recap where we are, so we're going to prove the smoothness rule next. So we're going to prove the smoothness rule. So remember, we have two complexity functions, f and g. So let there be two complexity functions. F and G, where F is big O of G, when n is a power, n is a power of an integer constant, integer constant b greater or equal to 2. So remember the characterization that we need for the smoothness rule is as follows. If f is asymptotically non-decreasing, it's asymptotically non-decreasing, and g is smooth, then it has to be unconditionally that f is big O of g. That's the smoothness rule. That's at least the way, this is one possible smoothness rule. So what we have at our disposal is that f is asymptotically non-decreasing and that g is smooth. And we know this is true for certain values of n. In this case, that n is a power of b. So what I'm going to do is I'm going to show you that if you make this presumption about n, and you know that f is big O of g for these values of n, you could just drop all of this, presuming that f is asymptotically non-decreasing and f and g is smooth. And as we previously established, there's many common complexity functions that are in fact smooth. Like we talked about constant functions, log base 2 of n, we talked about n to the power of k. These, for example, are all smooth functions. So meaning that you could use this as a tip or trick to analyze your algorithm's running time in a much simpler manner without having to cut corners. So you're not actually cutting corners. That's the beautiful part about it. You're cutting corners in the best of ways, meaning that you're not losing anything. If your goal is to get a big O statement that involves all values of n, this smoothness rule will allow you to do that. Is that beautiful? So you don't have to go cutting things in floors and ceilings. You don't have to do all that dirty work. If you want to presume, for example, that n is a power of 2, if f is an asymptotically non-decreasing function and g is smooth, then you're allowed to do that. And it gives you this it gives you this conclusion at the end. So it's very slick. So you could use this to simplify some of your time complexity analysis if it is actually relevant for what you're doing. So for example, like I said, there's some algorithms like merge sort, binary search, many of them that involve cleaving things into halves. The smoothness rule actually makes the analysis go a little bit smoother. So anyways, let's do the proof now. So I'm going to have some setup for this, and I warn you in advance. There's going to be a lot of variables that are going to be kicking around, but it's not going to be too bad. I'm hoping that I'm going to have some bookkeeping at the beginning that's going to make this work. I'm going to be invoking these definitions to make this possible, okay? So just follow me very carefully. So we know that function f is big O of g, right? We know this. This is given to us when, but we know only when n is a power of b. n is a power, that says power by the way, it looks like power, power, it's the power of b, okay? It's the power of b. So that means that there has to exist those constants, right? The constants we get for the big O notation, but it's only for these specific values of n, right? So that's going to play a big role in this proof. So there exist constants C, I'm going to call them C1 and N1, which is positive integer, and N1, which is a positive real number for C1, and N1 is going to be a positive integer, such that for all n greater or equal to n1, where n is a power of b, that's an important bit of this, n is a power of b, then we know that f of n is less than or equal to c1 times g of n. So that's the first thing. And this is true for all n where n is a power of b, but it has to, they're at least n1. So let's talk about where we're going next with this. So now we remember, we know f is asymptotically non-decreasing and we know g is smooth. So we would like to use these facts, okay? Like I said, we're going to have a little bit of bookkeeping, but once we get past the bookkeeping, you're going to see that this is actually going to come out quite smoothly, as I like to jokingly say. So this is actually a really good exercise on understanding why the types of functions actually really do matter. So knowing that a function's increasing, if it's non-decreasing, like these are important details. So when somebody tells you, Dan, all that calculus that we learned, like, Dan, it didn't really matter. Like, say, for example, you took a calculus class, or if you didn't, that's okay. I've gone through most of the things you get and need to know here regardless. But often a common complaint of CS students is that, why do we have to take this calculus class? If you really want to understand the whys of some of these rules that you learn sometimes in your lectures, this is why. It's because some of the reasons why you need to know, like, how a function's increasing, decreasing, etc. These are all important elements to prove statements like the smoothness rule. Because you need to know what a function, like what we're even talking about, right? And calculus gives you an intuition for how that works. But that's just an aside here, okay? So next function g is smooth, right? So we have two properties we can use. Function g is smooth. But remember, we already proved that it's b-smooth, right? Implying g is b-smooth. Remember, we proved this. Where we're constants, so we're going to have constants, C2, which is a positive real number, and N2, which is a positive integer, exist. And it has to be that g of bn is less than or equal to C2 times g of n for all n greater or equal to n2. Remember, this is part of the definition of b-smooth, right? You might recognize this for, like, when we had smooth, it was just 2 times n. Now it's just bn. Do you see why we might need this b, okay? So this is one of the reasons. So anyways, now we have this. Now we're going to invoke the fact that f and g are both asymptotically non-decreasing. Both f and g are asymptotically non-decreasing, right? And remember, the main reason why we know g is asymptotically non-decreasing is because it's smooth. It's one of the conditions for being smooth. non-decreasing. So that means that there actually has to also exist other constants. There exist 2 points, n3 and n4. I'm going to give them those names. So n3, n4, which are both going to be positive integers, exist such that f of n is less than or equal to f of n plus 1. And g of n is less than or equal to g of n plus 1 for all n greater or equal to 3, sorry, n3, for all n greater or equal to n3, and n greater or equal to n4, respectively. So these are both also going to be important because we need to make sure that we get big enough values for the input so we can ensure that, that we are on that one side where it's always going to be going up or it's going to be plateauing. So we got all the bookkeeping. Now watch this. This is going to be one of the fun examples here where I'm going to pick a really interesting constant for n0. So watch this. Now I must stress that this isn't the most elegant or optimized version of this. But this will certainly cut it. This will cut the mustard, okay? So I'm going to pick n0 as follows. Now I'm going to pick n0 first, which is kind of strange because they're used to be picking c first. But I'm going to pick it this way. The reason why is because we have all of these inequalities, right? All of these inequalities, they all have this property that they need to be for a sufficiently large value for some input. So what I'm going to do is I'm going to pick it so that it is large enough for all of the inequalities to be true. But I'm going to throw b in there as well, just to make sure it's really going to be big enough, okay? Now watch this. Now, this is why I need this to be the case, because I'm going to have a whole bunch of inequalities I can now write out in use when I make n0 this big. So now I'm going to use a property that we have at our disposal relating to the powers of b. So this is another key part of this. Then observe that for any n greater or equal to n0, and I must stress to remember that n0 is greater or equal to 1. So just keep that in mind. There exists integer k. So this is a claim I'm making to you, but I at least hope that it should be clear enough to you where it comes from. There exists integer k greater or equal to 0, such that I'm going to be able to sandwich things like this. Such that b to the power k, so some power of b, is going to be less than or equal to n. But this one has to be sandwiched between this power of b and the next power of b. But this cannot exceed b times n. Why? Well, just think about it. If I have a power of b here, suppose that this was indeed a power of b, then it would be equal. But now, suppose that it actually isn't. It's somewhere in between the two. Now, if it was the case that n was a power of b, say it's b to the k, then b times n would just be b to the k plus 1, right? But we know that the next power of b is definitely going to be bigger than n. Hopefully you see this. So I'm sandwiching it like this deliberately because we are dealing with asymptotically non-decreasing functions, so we can look at their inputs. And we can make statements about if it's smaller or larger or equal at those points. So I'm going to need this to help this out. So, and we're going to have the following. So you're going to watch this be rather slick. So watch this. So watch this. I was about to grab that eraser. Let's grab this one. So now this is where all of this is going to come together. It's all going to come together now. I'm giving you no BS here. It's all going to come together now. So we have that we could sandwich n in between different powers of b. And as follows. So watch this. And we know that now we know f of n is less than or equal to f of b of k plus 1. This is because f is asymptotically non-decreasing. This we know. But this right here, remember, this is a power of b here. So remember, this is a power of b. We have something that we could say about powers of b when n is a power of b. Remember, we have the big O claim. C1 times, this has to be less than or equal to C1 times, not F, it's going to be G. This is how we're going to bridge from F to G. C1 times B to the K plus 1. This is because F is big O of G when N is a power of B, or power of B. Remember, we have this. Then next, because of the way I sandwiched the powers of B, notice that B to the K plus 1 is less than or equal to B times N. So I could say this. So C1 times G of Bn. So this is because G is asymptotically non-decreasing, right? And we know that B to the K plus 1 is less than or equal to B times N. Now, this has to be less than or equal, because remember, now I know that G is smooth, right? But that means it's B smooth. But look what we got right there. We have G of Bn, and we established that that's going to be less than or equal to some constant times G of n, right? So I'm just going to put that in. C1 times C2 times G of n. And this is because G is smooth. And as we established, smooth functions are B smooth. And lastly, I'm just going to put this all together. So I have C1 times C2 times G of n. But what could you pick for C then? Now you have f of n is less than or equal to C1 times C2 times G of n. Well, it's right here. There's C right there. So we're going to just select C is equal to C1 times C2. Therefore, C and N0 have been selected. So just to kind of recap everything, have been selected so that f of n is less than or equal to C times G of n for all n greater or equal to N0. Therefore, we have the definition of big O, right? Therefore, f of n is big O of G of n unconditionally. And we're done. This is unconditionally. It looks like it melted, like somebody put some cheese on top of something that maybe shouldn't have got melted with cheese. That says unconditionally. And that concludes the proof for the smoothness rule. So now we know that the smoothness rule is in fact true. If there are any questions, I'm happy to answer those. But that's how we can prove this. This is one proof for the smoothness rule. Very slick, right?